an IITG person promises only what he can deliver, and an IITG person delivers what he promises.
So, today we are going to study about this multi degree of freedom systems. So, last class we have studied how to determine the equation motion of a multi degree of freedom system, and you know different methods of finding the equation motion. The methods are either you can use the inertia based principle, that is Newton's method, or energy based principle, that is Lagrange principle, or Hamilton principle, or extended Hamilton principle. Also I have started another, I told you another method to find the equation motion, that is by using the flexible influence coefficient method, and we have seen the definition of flexibility influence coefficient. So, two different types of flexibility influence coefficient I told. One is the displacement flexibility coefficient and other is the stiffness flexibility coefficient. So, that flexibility influence coefficient Aij, last class I have defined it as the displacement at I. So, it is the displacement at I due to a unit force applied at j when the other forces are 0. So, Aij is the flexibility influence coefficient. So, this is the displacement flexibility influence coefficient, and we have defined this flexibility influence coefficient as the displacement at I due to unit force at j when the forces at other places are 0. Also we have taken one example to derive or to find the influence coefficient. So, in that example I have taken 3 mass. So, they are placed at same distance, that is L. So, this is L, L and L. So, I can take the mass, same mass M1, M2, M3 or M. So, I have taken, so this is station 1, this is station 2 and this is station 3, and I have found the influence coefficient A11, A12, A13, A21, A22, A23 and A31, A32, A33. So, A11 is the displacement at 1 due to a unit force at 1. Similarly, A12 is the displacement at 1 due to a unit force applied at this position, that is 2, and A13 is the displacement at 1 due to a unit force applied at 3. Similarly, A21 is displacement at 2. So, this is the displacement at this position, that is 2, when a unit force is applied at 1. Similarly, A22 is the displacement at 2 when a unit force is applied at 2. Similarly, A23 is the displacement at 2 when a unit force is applied at 3 and the forces at other places equal to 0. Similarly, A31 is the displacement at 3 when a unit force is applied at 1 and the forces at the other two places are 0. Similarly, A32 is the displacement at 3 when a unit force is applied at 2 and forces at other places are 0. Similarly, A33 is the displacement at 3 when a unit force is applied at 3 and the other forces are 0, and I have derived that those expressions by drawing the bending moment diagram. So, displacement of a, so I can consider this as a cantilever beam with 3 mass, So 1, 2 and 3 mass, and when a unit force is applied at here, so I can find the displacement. So I can find the displacement at this position by applying a unit force at this. So that thing can be obtained by drawing the bending moment diagram. So the bending moment diagram, so here the bending moment diagram will be like this. So this is length is 3L, so this is 3L. So to find A11, one can find A11 by finding the area of this diagram, area. So area of this diagram equal to half 3L into 3L, and taking the moment of this area. So moment will be, so it is acting at a length of 2/3 of 3L. So this becomes, so 3 cancel, so this becomes 9L by, so this by 1 by EI. So this becomes 9L by EI. So in this way we have determined the influence coefficient A11, so which is equal to 9L by EI. Similarly, you can determine the other coefficients also. For example, let me determine A21. So A21 is the displacement at 2 due to a unit force at 1 and forces at other places equal to 0. So when a unit force is applied here, so the displacement can be obtained from this bending moment diagram. So this is the bending moment diagram, length is 3L. As you are applying a unit force here, the bending moment at this position will be 3L. So the bending moment at, or the displacement at this position can be obtained from this area, bending moment of this area. So you can obtain it, bending moment of this area. So A21 will be, so this area you can divide into two parts. So this is the rectangular part and this is the triangular part, and A21 you can obtain from this area first by taking the moment about this point for this rectangular part. So this rectangular part, this length is L, so this is L, and this to this length is L. So this area will be equal to 2L into L into moment. So you have to take the moment. So this distance is 2L, so it is at a distance L, and for this triangular part it will be half, this is 2L into, so this is 2L and this is also 2L. So 2L into 2L into, from this to this centroid of this point is at this. So this is 2/3 of 2L by EI. So this becomes, so this is 2L cube plus, so 2 cancel. So this becomes 2 and 2 4, 2 8. So 8L cube by 3 by EI. So this becomes 6 plus 8, this is 14L cube by 3 EI. So in this way, in the last class we have determined the flexibility influence coefficient of all the points. So we have determined the matrix, and that matrix is given by, so that matrix already we have seen, and that matrix is given by L cube by 3 EI into 27, 14, 4, 14, 8, 2.5 and 4, 2.51. So in this case you can observe that this Aij equal to Aji. That means A21, so this is A21 equal to 14, here A12 is also 14. Similarly A31, so this is A13 equal to 4 and A31 is also 4. Similarly A23 equal to 2.5 and A32 also equal to 2.5. So you can see that or observe that this Aij equal to Aji. So this is known as reciprocity theorem. Reciprocity theorem. So for a linear system, so this is a linear system we have considered. So for a linear system you can tell that this Aij, flexibility influence coefficient Aij equal to Aji, it means displacement at I due to a unit force at j equal to displacement at j due to a unit force at I. So, to prove that thing, let us take a system. So, let this is a system or the system what you have just now you have derived. So, let us take this system and you apply a force, apply unit or apply a force at ith station. So, let this is the ith point, applying a force at I, applying a force F I at I. So, the work done will be equal to half force into displacement. So, when you are applying a force F I here, so let this is the F I force is applied here. So, the and other places you are not applying any force. So, the displacement at this position will be F I into displacement will be F I into A I I, as due to a unit force at ith station the displacement will be A I I. So, due to a force F I applied at ith position the displacement will be F I into A I I, and other places at force equal to 0 the work done will be equal to summation of force and displacement at all these places. So, as the forces at other places are 0, so the work done will be equal to half into, so this is the force F I into displacement F I into A I I. So, this becomes half F I square A I I. Now, after applying this force F I, let again we will apply another force F j at jth point. So, let this F j force is acting at j. So, due to this force F j, this point j will undergo a displacement of F j into A j j, and this ith point which has already a displacement of A I I will have a displacement of A I j. A I j is the displacement at I due to a unit force at j. So, the total displacement at this position due to this force F j will be A I j into F j. So, the work done will be due to the displacement at this position and due to the displacement at this position. So, the displacement at this position is A I j F j, and this position it is F j into A j j. So, the total work done will be half F I square A I I plus half F j into F j into A j j plus half F I. So, already a force F I is acting at this position and this point is undergoing a displacement of A I j into F j. So, due to that the force or due to that force the work done will be F I into F I F j I into A I j, force F j into A I j. So, this becomes, so the work done W equal to half F I square A I I plus half F j square A j j plus, okay. So, this point will under force into displacement. So, this becomes F I. So, this becomes F I F j A I j. Now, let us alternate the application of force. Let us first apply the force at F j. Let us first apply the force F j and then apply the force F I. So, if you apply the force F j first, then the work done will be equal to half F j square A j j, and by applying a force F I after that we will have a displacement F displacement of A j I. So, this is the displacement at j due to a unit force at I, and as I am applying a force Fi, so this point will undergo another displacement of Aji into Fi, and here a force of Fj is applied to the system. So, this the work done will be equal to, total work done will be equal to half Fj square Ajj plus half Fi square Aii plus half plus force into displacement. So, this is, so this force Fj into Aji into Fi. So, we can, so work done if we are applying the force at J first and then at I, then the work done is half Fj square Ajj plus half Fi square Aii and plus half Fj Fi into Aji. So, from these two, as the work done in both the cases will be same, because it does not depends on the application of the force or the, so we can write, so we can equate this A and B, and we can write this half Fi square Aii plus half Fj square Ajj plus half Fi Fj Aij equal to half Fi square Aii plus half Fj square Ajj Fj square Ajj plus half, there is no half here. So, Fi into Fj into Aji. So, this is Aji. So, by equating this you can cut this and you can see that Aij equal to Aji. So, for a, so this is the reciprocity theorem, and for a linear system you can have Aij, that is flexibility influence coefficient Aij equal to flexibility influence coefficient Aji, that is the displacement at I due to a unit force at J equal to a displacement at J due to a unit force at I. So, this is the reciprocity theorem, and now we will study about the stiffness matrix. Stiffness matrix or property of the stiffness matrix of a system. So, in previous systems we have written the stiffness matrix K. Let us take a 3 degree of freedom system. So, the stiffness matrix K can be written as K11, K12, K11, K12, K13, K21, K22, K23 and K31, K32, K33. So, this stiffness matrix, this K11 or K11 can be defined as, so this is the force required at 1, this is the force required at 1 to have unit displacement at 1. So, this is the force required at 1. So, this is the force required at 1 to have unit displacement at 1, while the displacement at other places equal to 0. At other places equal to 0. So, similarly, Kij you can define as force required at I to have unit displacement at j when the displacement at other places equal to 0. This K12, so this first column, so this first column will represent, so this is force required at 1, 2 or 3 to have unit displacement at 1, while displacement at other places equal to 0. Similarly, this K second column will represent the displacement force required at 1, 2 and 3 to have unit displacement at 2, and similarly this third column will represent the force required to have force required at 1, 2 and 3 to have unit displacement at 3, while the displacement at other places equal to 0. So, let us take a example. So, let us take a system with 3 mass and springs, and let us determine the stiffness matrix of the system. So, this is K1, this is K2, this is K3, and the system is supported on some wheels. Okay, so the system has this is mass m1, this is mass m2, and this has mass m3. So, to find K11, that is force required at 1 to have unit displacement at 1, we can draw the free body diagram of all these 3 masses and we can find that thing. So, in case of K11, so it is the force required at 1. So, this is 1, this is 2, this is mass 3. So, force required at 1 to have, so this is the force required at 1 to have unit displacement at 1, and displacement at this position and this position, that is at 2 and 3 should be 0. So, to draw the free body diagram, let us draw the free body diagram to determine this. So, this is mass 1, mass 2, and this is mass 3. So, we have to find what is the force required at 1 to have unit displacement at 1. So, if it will have a unit displacement at 1, so this spring will be stretched by an amount 1, and so it will exert a force in opposite direction, that is magnitude will be equal to K1. Similarly, the second spring K2, so this spring will be compressed by 1 as this point is not moving, at the second point is not moving. So, this will be compressed by 1, and so it will exert a force K2 in this direction. So, for unit displacement of this mass 1, so these 2 springs will be giving a force K1 plus K2 in this direction. So, they will exert a force in this direction. So, to have that displacement, one has to apply a force F1. So, that force, one has to apply a force F1 equal to K1 plus K2 to have unit displacement at 1 and displacement 0 here and 0 here. So, this K11 become K1 plus K2. So, K11 equal to your F1. So, this F1 equal to K1 plus K2. And now, let us see the second mass. So, as the displacement of the second mass equal to 0. So, this spring K2 due to this motion, unit motion of mass 1. So, it will compress this mass m2. So, it will exert a force K2 on this mass m2, and this K3 spring, as there is no motion of mass 2 and 3. So, this K3 spring will have no motion. So, it will not exert any force on this. So, the total force acting on m2 equal to K2. So, to have or due to this force, so the mass should move in towards right, but to prevent its motion we should apply a force F2 in this direction. This force F2 equal to K. So, that is equal to K force required at 2 to have unit displacement at 1 and displacement at other places equal to 0. So, that is K21. So, this will be equal to F2 and it is equal to K2. So, this will be equal to minus K2 because we are taking this the direction towards right positive. So, as we have to apply a force in the opposite direction. So, one has to write this is equal to minus K2. Similarly, for mass 3, so this is K3 and this is spring K4. So, as there is no motion of this mass 2 and 3, so the spring will So, the spring force acting on 3 equal to 0 and the spring force acting on 4 equal to 0. So, no force is required. So, as there is no force acting on this mass m3, so no force is required to have it 0 displacement. So, F3 will be equal to 0. So, this K31, that is force required at 3 to have unit displacement at 1 and displacement at other places equal to 0 will be equal to 0. Similarly, we can find K applying a K, we can find K12, K21, K12, K22 and K23, K32. So, for this the second mass will have to undergo a displacement of unity and other two masses will be at their equilibrium position. So, they will have no motion. So, for that I can draw the free body diagram. So, in this free body diagram, so mass, so this mass m1 will have 0 motion and mass m2 will have unit motion. So, it will move unity and mass m3 will have also 0 motion. So, it will also not move. So, we have to find what is the force required to have this configuration. So, in this case I can draw the free body diagram. So, this as this mass is not moving or it is stationary. So, the spring will not exert any force on this side, but as the second mass is moving, the spring K2 will be pulled by an amount K. So, the spring K2 will pull this mass m1 with a force K2. So, a force K2 will act on this mass m1. So, to prevent this motion of this mass 1 or to have 0 displacement of this mass 1 when a force K2 is acting on this. So, we have to apply a force or one has to apply a force F1 to have this motion, have 0 motion here. So, this F1 equal to K12. So, this will be equal to, so as this is acting in opposite direction. So, I can write K12 equal to minus K2. Similarly, when this mass m2 has unit displacement and mass m1 and m3 are 0 displacement, the spring K2 will be pulled by this mass m2. So, the spring K2 will exert a force in opposite direction and so the free body diagram will be like this. So, it will be K2 and in the right side. So, the spring K3, for the spring K3, the K3 spring will be compressed by this motion of mass 2 and as there is no motion of mass 3, the relative motion of spring K3 will be unity. So, the spring K3 will exert a force in opposite direction and this force will be equal to K3, K3 into 1. So, that is equal to K3. So, a total force of K2 plus K3 is acting on mass 2 to have unit displacement, a force K3 and K2 is acting. So, to have that motion one has to apply a force in this direction. So, that is your F2 and this force should be equal to K2 plus K3 and that is K22. So, K22 equal to F2 equal to K2 plus K3. Similarly, this mass 3, at this time the mass 3 is subjected to a force due to the spring K3. So, the spring K3 will push this mass 3 with a force of K3 as the relative motion of the spring equal to 1 minus 0, that is equal to 0 and as there is no motion of this mass m3. So, this K4 force or force due to the spring K4 equal to 0. So, the mass 3 will be subjected to a force of K3 only and that force. So, this is K3. So, to have this body in equilibrium position, the force required is K3 in opposite direction. So, that is F3. So, this K32 equal to F3 equal to minus K3. Similarly, one can find K13, K14, K23 and K33 by drawing the free body diagram when the mass 3 is having unit displacement and mass 2 and mass 1 having 0 displacement. So, this is mass m1 having 0 displacement, mass m2 having 0 displacement and mass m3 having unit displacement. So, when mass m3 have unit displacement, spring K3 will be pulled by unity. So, it will exert a force in opposite direction, that is K3 in this direction. Similarly, the spring 4 K4 will be compressed by unity and it will exert a force also in opposite direction. So, that is K4. So, one has to apply, or the force required to have unit displacement at 3 will be equal to K3 plus K4, and so that is equal to K. So, this is the force F3. So, that is equal to K3 plus K4. So, this force is required to maintain or to have unit displacement at this one. So, force required at 3. So, this is K33, force required at 3 to have unit displacement at 3. So, this is equal to K3 plus K4. Now, to find K23, let us see this mass free body diagram of this mass m2. So, in this case, to have unit displacement at 3, the spring K3. So, in this case, to have unit displacement at 3, the spring K3 will pull mass m2 by a force K3 in towards right. So, this spring K3 will pull this mass towards right by a force K3, as there is no motion of mass m2 and m1. So, this force or the spring K2 will not exert any force. So, the total force acting on mass m2 equal to K3 towards right. So, the force required to have this motion will be in opposite direction to this, and this is equal to F2 and this F2 equal to K23. So, K23 equal to F2 equal to minus K3. Similarly, for mass 1, as there is no motion of this spring K2 and K1. So, there is no force acting on mass m1. So, no force is required to have this motion. So, K13 will be equal to 0. So, in this way we have determined all the stiffness coefficients. So, by arranging those stiffness coefficients, one can write. So, this matrix equal to, so this matrix becomes K matrix equal to K1 plus K2 minus K2 0, and this is minus K2 K1 K2 plus K3. So, this is K2 plus K3 and minus K3, and this is 0 minus K3 and K3 plus K4. So, here also you can observe that Kij equal to, so it is also follow the reciprocity theorem, that is Kij equal to Kji. So, for a linear system, so you can see that this stiffness Kij, so K12 equal to K21, similarly K13 equal to K31 and K23 equal to K32. So, Kij equal to Kji. So, from the definition of the stiffness influence coefficient, you can determine the influence coefficient or all the elements of the stiffness matrix in this way. So, in this case, in this example, we have first drawn the free body diagram of these 3 masses, and we have found the force required to have unit displacement. To find K11, we have applied a, so to find K11, so we have checked what is the force required to have unit displacement at 1 and displacement at other 2 places equal to 0, and we have found that is equal to K1 plus K2, and similarly we have found K21. So, in this case we have seen that this mass is subjected to a force K2 to have a unit displacement at 1. So, as this mass is subjected to a force K2 to have it in equilibrium, the force required at station 2 equal to minus K2. Similarly, we have seen that at this position there is no force acting on this mass 3. So, K31 equal to 0. So, in this way one can determine the elements of the stiffness matrix by finding the force required at station at ith station to have force required at ith station to have unit displacement at jth station when the displacement at other places equal to 0. Now, till now we have studied how to determine the equation motion of the multi degree of freedom system. So, first we know by using the Newton's method we have determined the equation motion, Newton's method or D'Alembert principle, and then we have used Lagrange method, and next we have applied the extended Hamilton principle to determine the equation motion. Also we have studied this influence coefficient method. Now we have studied this influence coefficient method to determine the mass, to determine the stiffness matrix and the flexibility influence coefficient matrix of the system. So, you can observe that this displacement flexibility coefficient matrix equal to 1 by k, that is 1 by the stiffness matrix or reciprocal of the stiffness matrix. So, this is equal to k inverse. So, influence coefficient matrix or displacement influence coefficient matrix or the stiffness influence coefficient matrix, they are related by this formula, and by finding this displacement coefficient matrix or stiffness matrix one can write the equation motion by writing this mx double dot plus kx equal to 0. So, already we have seen this is the free vibration or this is the equation motion for free vibration of a multi degree of freedom system, where m is the mass matrix, k is the stiffness matrix and x is the displacement vector. So, either one can write the equation in this form or one may write this equation by pre-multiplying k inverse. I can write this equation in this form. So, it will be k inverse m x double dot plus k inverse k x equal to 0. So, k inverse k equal to I and this k inverse equal to A matrix. So, A m x double dot plus, so this is I x equal to 0. So, if you know the flexibility influence, displacement flexibility influence coefficient, so by multiplying this with mass matrix you can find another matrix, that is A x double dot plus I x equal to 0. Proceeding in the previous case to find the normal mode of the system. So, in this case also we can substitute this x equal to, so we can substitute this x equal to x sin x equal to x, so sin omega t, or so by substituting this thing in this equation, so x double dot will becomes minus omega square x. So, this equation becomes, so I can write this equation a minus a omega square plus I x equal to 0. So, in this way one can write this equation and you can, so minus a omega square plus I x equal to 0, or I can write this equation in this form a minus 1 by omega square I x equal to 0, or this equation can be written as a minus lambda I x equal to 0. So, in this case in this case this lambda equal to 1 by omega square. So, if you are finding the eigenvalue of matrix A, so this will give you 1 by omega square, but in the previous case when you have taken the equation in this form mx double dot plus kx equal to 0 and you have multiplied it with minus m inverse, then you got this equation m inverse kx equal to 0. That time also we have written this as A. So, it was reduced to this form A plus lambda I x equal to 0. So, in this case this lambda equal to omega square, in the previous case we have seen. So, the eigen value of this matrix A equal to omega square, and here if you are proceeding from the flexibility coefficient, displacement flexibility coefficient, you will get a eigen value which is reciprocal of the actual eigen value of the system. So, in this case the highest frequency will correspond to the lowest eigen value, and the lowest eigen frequency will or eigen value will correspond to the highest frequency of the system. So, you can solve the problem either from this by using the stiffness matrix method or by using this displacement influence coefficient method. In case of displacement influence coefficient method, if you proceed, so you will get the eigen value which is equal to reciprocal of this omega square, and in this case you can find it lambda equal to omega square. So, let us see the orthogonal properties of these eigenvectors. Orthogonal properties of eigenvector. So, we have already seen that these eigenvalues correspond to the square of the natural frequency, and eigenvectors correspond to the normal modes oscillation of the multi degree of freedom system. So, for the ith mode, I can write this eigenvector xi is this eigenvector xi for the ith mode correspond to the normal mode of the ith mode, and xj will correspond to the normal mode of the jth mode. So, one can show that these modes ith mode and jth mode are, or these modes are orthogonal with respect to the mass matrix and stiffness matrix of the system. So, in this case we are assuming that this mass matrix and stiffness matrix are symmetric matrix. So, already we know that the equation motion can be written in this form mx double dot plus kx equal to 0 by substituting. So, mx double dot I can write this small mx double dot plus small kx. So, plus kx equal to 0, I can substitute this x equal to x sin omega t, and I can write this equation minus m omega square minus m omega square x minus m omega square small x I can write, or capital X also I can write, minus m omega square x will be, or plus k x equal to 0, or I can write this k x equal to m omega square x. So, for ith mode I can write this k x I will be equal to lambda I m x I, where this lambda I equal to omega I square. So, the previous case this is omega square. For ith mode I can write this equation equal to k x I. So, it will be k x I sin omega I t will be equal to m omega I square x I sin omega I t. So, this sin omega I t will cancel from both side. So, you can write this k x I. So, this thing can be written k x I equal to lambda I m x I. So, here lambda I equal to omega I square. So, now pre-multiplying this transpose of the jth mode. So, I can pre-multiply this equation by x j dash. So, this is the transpose of jth mode. So, x j dash k x I will be equal to x j dash lambda I m x I. or this thing can be written xj dash k xi equal to lambda I into xj m xi. So, let this is equation A. So, let us start from the jth mode. So, I can write for the jth mode k xj will be equal to lambda j m xj. So, let me pre multiply this by x I transpose. So, this is x I transpose. So, x I transpose k x j will be equal to x I transpose lambda j m x j. So, I can write this x I transpose. So, this is x I transpose k x I transpose k x j. So, this x I transpose k x j equal to lambda j into x I transpose m x j, x I transpose m x j. So, now from this equation A and B, from equation A and B one can write equation, this is equation B, and equation A is written in this form x j dash k x I equal to lambda I x. So, you can see this thing. So, this is lambda I x j. So, this is x j dash. So, this is x j dash m x I. So, this is equation A. Now, if the stiffness matrix and mass matrix are symmetric, then you know that x I dash k x j will be equal to x j dash k x I and x I dash m x j equal to x j dash m x I for symmetric. So, this is for symmetric. So, this is for symmetric mass and stiffness matrix. So, from these two, by subtracting A from B, so I can write. So, if you subtract this thing, so this becomes left side becomes 0. So, 0 equal to lambda I minus lambda j into x I dash m x j. So, but this lambda I minus lambda j, that is these eigen values are distinct numbers. So, lambda I not equal to lambda j, and as lambda I not equal to lambda j, then this x I, so it shows that x I dash m x j equal to 0 if I not equal to j. So, when I not equal to j, this x I dash m x j equal to 0. So, this shows the orthogonal property of these eigen vectors. Similarly, you can show that x I dash k x j also equal to 0. So, this shows the orthogonal property of this mass, orthogonal property of these eigenvectors or the normal modes, orthogonal property of this eigenvector x I and x j or normal mode x I and x j. So, this is orthogonal property of the normal mode, orthogonal property of this normal mode. So, when I equal to j, so this will reduce to, so this will reduce to, so when I equal to j, so when I equal to j, you can see that, so this part equal to 0, so it satisfy this equation. So, when I equal to j, this x I dash m x j will be equal to x I dash m x I and x I dash k x j equal to x I dash k x j. So, these are known as, so this is known as generalized mass. So, this will give a diagonal matrix and this diagonal matrix is known as the generalized mass and this is known as the generalized stiffness matrix. So, this will give the generalized mass matrix and this will give rise to generalized stiffness matrix. So, in this way you can obtain the generalized mass matrix and stiffness matrix by using the orthogonal property of this eigenvector or normal modes. So, let us take one example. So, let us take a system. So, in this system this is 2 m 0, mass matrix is 2 m 0 0 m. So, the equation motion is written in this form 2 m 0 0 m x 1 double dot x 2 double dot plus 3 k minus k k x 1 x 2 equal to 0 0. So, let us take this example and let us find the normal modes and check the orthogonality property of this system. So, in this case this is the mass matrix M and this is the stiffness matrix K. So, I can write this A matrix equal to M inverse K. So, either I can find this A matrix from this M inverse K, or I can write from K inverse M. So, when I will write A equal to K inverse M, the eigenvalue of this will give me 1 by omega square, and when I will take A equal to M inverse K, the eigenvalue lambda will be equal to omega square. So, let me proceed in this way by taking M inverse K. So, if A equal to M inverse K, so this matrix I can find. So, this matrix will becomes, so A equal to M inverse K, and this is equal to 3 by 2 K by M minus K by 2 M, this is minus K by M, and this is K by M. So, I can find the eigenvalue of this matrix. So, eigenvalue, so I can find this eigenvalue by finding the determinant of A minus lambda I equal to 0. So, this will give me lambda 1 equal to half K by M and lambda 2. So, lambda 2 equal to 2 K by M. So, lambda 1 equal to omega 1 square and lambda 2 equal to omega 2 square. So, the natural frequency of the system or the normal mode frequency of the system omega 1 will be equal to root over K by 2 M, and omega 2 will be equal to root over 2 K by M. So, to find the normal mode of this system, I can find this normal mode by finding the adjoint of A minus lambda I matrix. So, already you know this x equal to this normal mode x equal to adjoint of A minus lambda I. So, I can find this adjoint matrix. So, adjoint of A minus lambda I becomes K by M minus lambda 1, this is K by 2 M, and this is K by M and 3 by 2 K by M minus lambda I. So, for lambda I equal to lambda 1, so I can find this x I or x 1, I can find the first normal mode. So, x 1, so by substituting that thing and finding the adjoint of this thing, so you can find this x 1 becomes, so you will get 2 columns of this, and you can check that by substituting this lambda I equal to lambda 1. So, this adjoint matrix you will get 2 columns, and you can see that, or you can verify that normalized form of this, both the columns are same, and this normalized form of both these columns will give this A minus lambda I when you substitute this lambda I equal to lambda 1. So, you will get this. So, this is equal to 0.1, this is also 0.1, 1.0, 1.0 K by M. So, you can check that both the columns are same. So, your x 1 equal to, so x 1 equal to, by normalizing you can write x 1 equal to 0.51. Similarly, by substituting lambda I equal to lambda 2, you can find this x 2, and you can find the adjoint of A minus lambda I, and that will give you minus 1.5, 1.0, 0.5 k by m, or the normalized value of x 2 equal to minus 1 1. So, you got the normal modes. So, the first normal mode is x 1, this is 0.51, and the second normal mode is minus 1 1. So, after getting these two normal modes, you can now verify these normal modes are orthogonal. Now, you just find this x 1 dash m x 2. So, this will be equal to 0.51 into 2 m 0 0 m and minus 1 1. So, this becomes minus m plus m equal to 0. Similarly, you can verify that x 2 dash m x 2 equal to 0, x 2 dash m x 2 equal to x 2 dash m x 2 equal to 0, and x 1 dash k x 2 equal to 0, and x 2 dash k x 1 is also equal to 0. So, this shows the orthogonal property of these eigen vectors or normal modes. So, today class we have studied about finding the stiffness matrix of a multi-degree of freedom system, and from the definition of the stiffness matrix, each element of the stiffness matrix or the k I j element of the stiffness matrix can be defined as the force required at I to have unit displacement at j and displacement at other places equal to 0. And we have seen the reciprocity theorem of the influence coefficient, and also we have seen the orthogonal properties of these eigen vectors or normal modes. So, next class we will study the free vibration of multi-degree of freedom systems by using this modal analysis method.